Alright, this is really exciting because today I get to be the teacher. And today's lesson is Taylor Polynomials and Approximations. Now, Taylor polynomials are a way of making a function into, well, a linear polynomial. So ordinarily you'd have your function represented by f, like my personal favorite function, f of x equals e to the x. But when you put it in the form of a polynomial, you could arrange it into a polynomial. Amazing, I know. The polynomial will be represented by p. Now the polynomial is going to have many different representations. You could have a first degree polynomial, which won't be as accurate as, let's say, a third degree polynomial. For instance, the first degree polynomial for e to the x is just p sub 1 of x equals 1 plus x. It's very simple. That's just the graph for a line. Now, we're going to take a look at how to turn these equations, these functions, into polynomials, and we'll even take it a step further and see how much more accurate it is when we find a higher degree polynomial for that function. Alright, so before we start, there are two rules. The first rule is that since the graphs have to resemble each other, they have to pass the same point, which is C. So you have to keep in mind that P of C equals F of C. The second rule is also very simple. It states that at least at C, both graphs have to have the same slope. So P prime C equals F prime C. Okay, so here we have example 1, which is f of x equals e to the x, my personal favorite function. So we're going to find the first degree polynomial, which is represented by this, it's represented like this. Now, a sub 0 is going to equal f of 0, because we're centered around 0 for this example, and a sub 1 is going to equal f prime of 0. So plug in 0 to e to the x, and it's going to be e to the 0, which gives you 1. And of course the derivative of e to the x is e to the x, so e to the 0 equals 1. That's really why e to the x is my favorite function, because e to the x, you derive it, and you get e to the x. Again, it's really perfect. Okay, so now we're going to write out our first degree polynomial for e to the x. So it'll be p1 of x equals 1 plus, hold on, I forgot the x up here. Okay. So plug it in, and it'll be it'll be 1 plus x. Truly, this is how you find a Taylor polynomial to any degree. Like if you need it's just plug and play depending on which degree of the polynomial you'd like. And now see, up here we found the first degree polynomial, and see right here, as you could see, it's just a line, 1 plus x. So what I want to show you is that the higher the degree, the more accurate, the more it approximates the function. So here we're going to find the third degree of Taylor polynomial of e to the x. So, I forgot that, it's centered around 0. Whoops. So basically we have the same situation as before. The beautiful thing about finding all the derivatives is all e to the x, so plug in 0, you get 1 for all your values. So there's your third degree polynomial for e to the x. Alright, so I mentioned that the higher the degree, the degree of the polynomial, the more accurate it is. And here, I wanted to show you graphically why that's the case. As you can see, the first degree polynomial is just a line. So it really just is the tangent line to the point at 0. And as you can see, the function for the third degree polynomial much more closely resembles the function for e to the x. And that's just the case. The higher the degree of the polynomial, the more closely that it'll resemble the function. Boy, I never realized how tiring and how stressful teaching is. Fortunately, I just have to show you one more thing, and that one thing is remainders. Now, the thing is that up to this point, we've been approximating the functions using Taylor polynomials. But the problem with approximating is that you're always going to have a margin of error. So the remainder is how you find the margin of error. Here, watch this. So we're going to take a look at a simplified version of Taylor's theorem, which is this. And I know this just looks like a bunch of letters, but let me explain. First, you have the actual value, which is f of x. That's very simple. That's the original graph. That's, in our first example, that was e to the x. That's just the actual graph represented in terms of x normally. Then you have the approximate value. The approximate value is what we've been finding by finding the Taylor polynomials. So we're good so far. We have an understanding of this. But next is the remainder. Now the remainder is just what's left over. When we make our approximation, there's a margin of error, and it's all left behind in this remainder. It's what remains. And that's how everything fits together. So now let's find out how to find the remainder and the margin of error. So this is the equation for the remainder. You should note that f sub n plus 1 is the nth plus 1 derivative of the function. So f sub n plus 1 of z over n plus 1 factorial times x minus c to the n plus 1. Alright, so when you're finding your margin of error, specifically the error, you're going to have to set bounds for the remainder. And this is how you do it. You'll take the absolute value and set it less than the absolute value of x minus c to the n plus 1 over n plus 1 factorial times the maximum value of f to the n plus, f sub n plus 1 of z. Now you'll notice that this looks almost exactly like the previous equation, which is great. Okay, example 3. The third Maclaurin polynomial for sine x is given by p sub 3 of x equals x minus x cubed over 3 factorial. Approximate sine 0.1 by p sub 3 of 0.1. Determine accuracy. Okay, so the first thing we're going to do is solve for the polynomial. So p of x. No, okay. Now you're going to find p sub 3 of 0.1. And yeah, the way you'll solve this is just by plugging in to the function that was given to you.
and that's the value of p sub 3 of 0.1. So that's the approximate value right there. Okay, so now we're going to find the remainder. So r sub 3 of 0.1, and remember the equation for the remainder. So, okay, in this case, it's going to be sine z, because when we're finding it, in this case, we're going to want the fourth derivative of sine. And in this case, sine is the fourth derivative of sine. I love trigonometry. So that's a fourth derivative. And then times 0.1 to the fourth over 4 factorial. Okay, so now we're going to need that second equation for the remainder, which was when it was in the absolute values, and this is how we find its bounds. So the remainder is going to equal 0.1 over 4 factorial. And see, remember that we have to have the maximum value of sine z, which in this case is just 1, so perfect. Oh, I'm sorry, it's less than or equal to this, and this is how we're going to find the bounds. So when we're finding this number, we're just going to plug it into our calculator. In this case, it's just 0.000004. Great number. Keep this number in mind too. You're going to need both of the numbers that I specifically boxed off to find your margin of error. So here's the function, the original function. So you're just going to plug your numbers in now. You have the value of the p. Your function, which is less than 0.099837, and that's your error. That's what the remainder helps you find.
Well, that's the end of everything. That's the end of the lesson. Thank you so much for watching. I hope I didn't put anybody to sleep. Just wanted to, I've learned a few things. I'm sort of not cracked up to be a teacher. Although, payday is Friday, so looking forward to that. Besides that, have a great AP test. I'll see you in class.